Hello everyone, welcome to today's video. Today we will be covering the fundamental trigonometric identities in an effort to be able to simplify and prove some other trig identities here. So we'll start by reviewing and verifying the fundamental trig identities, which they were the reciprocal identity, the quotient identities, the Pythagorean identities, and then the odd and even identities. And then we'll use those, like I said, to simplify some trigonometric expressions, and then we will use them to prove some trigonometric identities. So let's get into it here. We're just starting here with a list of all of the fundamental trig identities all in one spot. So just a summary of everything we've got so far. We'll go through one at a time and talk about each one. So we'll start with the reciprocal identities that, sine and cosecant are reciprocals of each other. Cosecant and secant are reciprocals of each other. And then tangent and cotangent are reciprocals of each other. And we can use this relationships to prove or verify some other stuff going forward. But first, let's verify these individually. And then we'll talk about how tangent can be written just as sine over cosine, and cotangent can be written as just cosine over sine. Again, we know that already that those should be reciprocals of each other, so that should make some sense. Then we'll take a look at the Pythagorean identities, that if you've got some things being squared and a 1 involved, if you get them in the right order, you have these relationships here. So we'll go through and talk about each one of those more carefully here in just a few minutes. And then we have the even and the odd identities, just using things we know about even and odd functions to get these relationships here. If we happen to have a negative argument, what can we say about some relationship here? So let's get into it. Each individual one, like I said, we'll start with the reciprocal identities. So what we have here is that the sine of theta and the cosecant of theta are reciprocals of each other. So we'll start with these guys here. And if you think back to when we talked about right triangle trig, we had all of these relationships here, and this is just quite literally how we defined all of these trigonometric functions using a right triangle. So if I have some angle theta down here, we just said, okay, the sine is the opposite over the hypotenuse. So I could write something like, thinking about my space here, sine of theta is equal to the opposite over the hypotenuse as just a quick shorthand here. And then I could say the cosecant, and this is just how this was defined, is the hypotenuse over the opposite side here. So the cosecant is of theta is the hypotenuse over the opposite. So just some different ways that we could write these as shorthand here. So if I want to look back here at the beginning and maybe show that sine of theta is equal to 1 over the cosecant of theta, well, maybe one way to convince you is just to look at the definitions we have here. The sine of theta is the opposite over the hypotenuse. The cosecant is the hypotenuse over the opposite. They are quite literally reciprocals of each other. So I don't think it's too big of a jump to just say, yeah, then we could just write this sine of theta is equal to 1 over the cosecant of theta because they are reciprocals of each other, and vice versa. I can write cosecant of theta as 1 over sine of theta because they are reciprocals of each other. But if that argument is a little too hand-wavy for you, which it might feel like, we can do this a bit more directly with some of this notation that we've written down here. So let me erase my scribbles. What we want to show here is that the sine of theta is equal to 1 over the cosecant of theta. Our goal going forward today is going to be able to prove some identities here. So here's a quick one. We're going to prove this reciprocal identity here. I'm going to start with the more complicated looking side, which is 1 over the cosecant, oops, not the cosine, the cosecant of theta. And I'm going to show that this is equal to the sine of theta using just some algebra and some other relationships here. But I know that the cosecant of theta can be written as the hypotenuse over the opposite. So I could write this as the length of the hypotenuse over the length of the opposite side. Well, now I've got a complex fraction, and one strategy that we'll see going forward is to simplify our complex fractions, and this simplifies to just take the reciprocal of the denominator to opposite over hypotenuse, which happens to be how we define the sine of theta. So this is equal to the sine of theta. So there is a more straightforward, direct approach to show that 1 over the cosecant of theta is indeed equal to the sine of theta. And you could use a similar approach with all of these different side length relationships to show that any of these are reciprocals of each other. I challenge you to do that. So there's my example of showing you that the sine and the cosecant are reciprocals of each other, and you could prove any other one of these 5 by using a similar argument. So there are reciprocal identities. We're allowed to use those going forward, and I promise you that we will. Next here we have the quotient identities, and this says that the tangent of theta can be written as the sine of theta over the cosine of theta, and the cotangent can be written as the cosine of theta over the sine of theta. So since we know from the previous slide that the tangent and cotangent are reciprocals of each other, all we need to do is show one, and then we'll get the other one for free since we know that they're reciprocals of each other. So let's look at the tangent side here, and we know that tangent is defined to be the opposite side over the adjacent side. So we can do something similar to like we did before, and we can use that relationship to show that the tangent of theta is equal to the sine of theta over the cosine of theta. So when we're proving identities, we usually start with the more complicated side. So I'm going to start with sine of theta over cosine of theta. And what I'm going to do is rewrite this using some of these relationships that I have here. I know that the sine of theta is, maybe I can color code as I go. The sine of theta is the opposite over the hypotenuse. So there's opposite over hypotenuse. And then we know that the cosine of theta is the adjacent over the hypotenuse. So adjacent over hypotenuse. So now if I want to simplify this, this is going to give me opposite over hypotenuse times hypotenuse over adjacent, simplifying this complex fraction here, multiply by the reciprocal of the denominator. Then we get the hypotenuses canceling out here, those h lengths, and we end up with opposite over adjacent. And that is quite literally how we define the tangent of theta. So there we go. We get a direct relationship between sine and cosine and tangent by just looking at what each piece represents in terms of side lengths of this right triangle, and we get that that is the tangent of theta. So there we go. You could do a similar thing to directly show that cotangent of theta is equal to cosine theta over sine theta. We also know that they are reciprocals of each other, so we just get the other one for free here. Next, we'll talk about the Pythagorean identities. So the first two here we talked about in terms of right triangle trig. Here we're going to use the unit circle to talk about these. It just makes more sense. But the way that we defined sine and cosine on the unit circle was that the cosine was related to this x value here. If we rotate our angle theta around the unit circle here, whatever the x value of this point is, so this distance here, you can think about it being this distance of this right triangle, that is our cosine of theta. X is the cosine of theta. And then the y value of this point here, which is corresponding to this vertical distance here, this vertical distance, gives us, the y value gives us the sine of theta. So that is just how that is defined. This point on the unit circle, x value, whenever you rotate some angle, the x value of that angle where it intersects the unit circle gives us the cosine of theta, and the y value of that point gives us the sine of theta. We just happen to notice now that this is creating a right triangle, and we can use that relationship since we are on the unit circle. We know that this is a hypotenuse of 1, that x squared, that is this distance here at the base, plus y squared, that is this distance here. The height of the triangle, the other leg, is equal to the hypotenuse squared, which just says x squared plus y squared is equal to 1. And if we use our new relationship now that the x value is equal to the cosine of theta, we would get cosine of theta being squared. I'm writing things very carefully right now, and then we'll simplify the notation. Plus y is equal to the sine of theta being squared is equal to 1. And then more traditionally, we use this notation here, that the cosine squared of theta is equal to, plus the sine squared theta is equal to 1. So that is the notational change there, but we'll see that maybe writing it in this kind of more direct form might be helpful when we solve stuff later, so keep that in mind. But here is the first of our Pythagorean identities here, that the cosine squared theta plus sine squared theta is equal to 1. And we can use this to prove the other ones here. So if I want to show that 1 plus the tangent squared theta is equal to the secant squared theta, what we can do is just start with the one that we already know is true, cosine squared theta plus sine squared theta is equal to 1. And we can go through and we can divide by whatever we want. If I divide both sides here, I have to think carefully about the one that I want. If we divide both sides by cosine squared theta, so this is the same as dividing both sides by cosine squared theta, cosine squared theta. Well, this simplifies to give us, let me go back to green. Cosine squared theta over cosine squared theta is just 1. Sine over cosine is the tangent, so sine squared over cosine squared of theta is equal to the tangent squared of theta. And 1 over the cosine squared theta, well, 1 over cosine we saw from those reciprocal identities as the secant, so 1 over the cosine squared is the secant squared of theta. So there we go. There is that identity there. We can just divide both sides of the kind of more straightforward Pythagorean identity by cosine, and we get what we want. Similarly, we could divide both sides. If I start with, let's see, change colors just for fun here. If I want to show this other relationship here, if I start again with, we'll start with cosine. Cosine squared, oh, I can't quite write here. Cosine squared theta. Oh my god. Cosine squared theta plus sine squared theta is equal to 1. Now if we go and divide both sides by cosine squared theta instead, I'm sorry, by sine squared theta instead, sine squared theta, sine squared theta, sine squared theta. Then again, from our reciprocal identities, we would get that cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared theta. Sine squared theta over sine squared theta is just 1. And then we know that 1 over sine is the cosecant, so 1 over sine squared theta is cosecant squared theta. And there is the other one that we were trying to show here. So by just using this unit circle, we can see that cosine squared theta plus sine squared theta should be equal to 1. And then we can get these other two identities by just dividing both sides by either sine squared theta or cosine squared theta. On the spot, I'll tell you that I don't have these other two memorized as well. If I'm doing a lot of trig stuff, then I tend to get them stuck in my head. But if I ever just need to double check, I just do exactly what I did here by starting with the one that I know and then dividing both sides by either cosine or sine to see if I get what I expect, and we can do some practice with that. We'll probably see in some of these examples going forward. But there we go. There's the Pythagorean identities for us. We are free to use them to solve things going forward. Now, as we look to simplify some expressions or prove some of these trig identities going forward, we might not see exactly these Pythagorean identities, but some sort of rearrangement of them. So let's just think maybe if we subtracted sine squared theta from both sides of just this straightforward Pythagorean identity here in terms of sines and cosines, then what we would get is that the cosine squared of theta is equal to 1 minus the sine squared of theta. And as we're working through some stuff later on, we might find 1 minus the sine squared of theta, and it will be important to know that we could rewrite that as just the cosine squared theta. Similarly, I could have subtracted cosine from both sides, or cosine squared theta from both sides, and we would have seen that we would have gotten sine squared theta is equal to 1 minus the cosine squared theta. So again, we might see something that looks like 1 minus cosine squared theta, and it's important to know that that's the same as the sine squared theta. And we could do this with all of the different ones up here. I could rewrite tangent squared theta as secant squared theta minus 1. Or I could write secant squared theta minus 1. Minus tangent squared theta, and that is equal to 1. So just different ways that we could subtract values here. So when we are working through these identities later, we can say, okay, that's not exactly something that I'm used to, but I could rearrange some of these identities that we are given, we know that are true, to get some of these other relationships here. So you'll see as we work through some of these, I might go off to the side, remind myself of the Pythagorean identity, simplify it, and see if we get what we expect or not. So next we'll take a look at the even and odd identities, and this just focuses on the even and odd properties of these trig functions in general, but we know that cosine is even, and we know that both sine and tangent are odd. So we'll go and take a look at some of these graphs here, and we'll show that those are true from their graphs. So if we take a look at this graph of cosine, what we're seeing is that if we're looking at pi over 4 and negative pi over 4, that they have the same output value, that it doesn't matter if the input is positive pi over 4 or negative pi over 4. In either instance, and I don't know why this picture that I stole has the approximated value, but these are both square root of 2 over 2 as their output values here. So we can see that the cosine of negative pi over 4, cosine of negative pi over 4 is equal to the cosine of pi over 4, because they both have an output value of negative square root of 2 over square root of 2, not negative, positive. And we can see that for any point on the graph. It's not just happening at pi over 4 and negative pi over 4, but if I focused instead on the pi value and the negative pi value here, we can see that the cosine of negative pi is equal to the cosine of positive pi. They both have an output value of negative 1. So just in general here, we can see that the cosine of negative x is equal to the cosine of x. Just by looking at the graph here, that always is true. We can also see that there's this reflection across the y-axis, this y-axis symmetry, and that is also a property of even functions. So there we go. We can see that the cosine is even, its reciprocal function, secant, must also be even. So what we'll see going forward is that if we have a negative argument, we can essentially ignore it and turn it into the positive version if that makes things easier for us. And same thing for secant, that we can think about just using the positive version, and that will make things easier. Right, next we will take a look at the sine function, and we'll show that it is odd here from its graph. So if we take a look here at the labeled values, we've got negative pi over 2 being at 1, and negative pi over 2 being at negative 1, and pi over 2 being at positive 1. So if we take a look here, what's going on is we've got the sine of negative pi over 2 is equal to the negative sine of pi over 2, which would be negative 1 in both cases there. Let me make sure I get my negative in there. So the sine of negative pi over 2 is literally negative 1, and then if we look at the sine of pi over 2, that's positive 1, and then make it negative, we get negative 1 either way there. So we can see that the sine of negative pi over 2 is equal to the negative sine of pi over 2. And we can do this with literally any point on this graph. So if I just pick a different color, and instead let's choose negative 3 pi over 2. So we're looking at the sine of negative 3 pi over 2. That is going to be the same as, if I look over to 3 pi over 2, you can see that there's this reflection through the origin now, not just across the y-axis. Y-axis is for even functions, but if you have this reflection through the origin, that's what is happening with odd functions here. So we can see that the sine of 3 pi over 2 is also equal, is equal to the negative, I got too busy talking there, is equal to the negative sine of 3 pi over 2, which here is positive 1. So the sine of negative 3 pi over 2 is quite literally positive 1. The sine of 3 pi over 2 is negative 1, but if we throw a negative in front, then we get back to positive 1. So here we can see that any points that we pick, we get this relationship being true. So just in general, the sine of negative x is equal to the negative sine of x. So there we go. We can see that the cosine is an even function. We can see that the sine is an odd function just by looking at their graphs here. But what we still have left to do is show that the tangent is also an odd function, and we can do that by just using the relationships that we have in front of us here. So let me make a little bit of space. We'll just make these guys smaller. Oops. And maybe move them up here. Don't know why it does that. And we'll move that guy over there just so they're still around. But if we want to now show that tangent is odd, so we can take a look at the tangent of negative theta. And what we want to do here is show that it is the same as the negative tangent of theta. So we can just use some of our fundamental identities here to show that. This is going to be, if I now maybe rewrite things in terms of sines and cosines, this is going to be the same as sine negative theta over the cosine of negative theta. And now I can just use the properties of sine and cosine. They're even and odd properties. I know that I can rewrite the sine of theta as the negative, I can rewrite the sine of negative theta as negative sine of theta. And I can rewrite cosine of negative theta as the cosine of theta. And now this is quite literally negative tangent of theta. If I just rewrite this portion here as tangent theta and then stick that negative in front, that's what we get. So there we go. We've got that tangent of negative theta is equal to the negative tangent of theta every time, and so we get the same relationship for its reciprocal function as well. So now we know cosine and secant are even functions. Sine, cosecant, tangent, and cotangent are all odd functions, and we can use these properties if we see some negative values in the arguments. So all right, now it is time to hop into some examples here. So for these first ones, we are asked to simplify the expression into a single trig function with no fractions. So it's important to read the instructions. Sometimes you're asked to do different things. Sometimes they want a single trig function with no fractions. Sometimes they just want no fractions, and it doesn't need to be a single trig function. So just pay attention to what the instructions are saying to make sure you get to where you're supposed to go. So for this first one here, we've got the secant squared x times cotangent x times cosine of x. If I'm asked to simplify this into a single trig function with no fractions, well, I don't see any fractions yet, but we might end up getting some. So I'm just going to rewrite things in terms of some of these fundamental identities. I know that the secant squared of x is the same as 1 over the cosine squared of x. And then I know that I can rewrite cotangent x as cosine x over sine x, just using that quotient identity. And then cosine of x is cosine of x. So cosine of x here is just cosine of x. Maybe I rewrite that, I can write that better. Maybe I rewrite that as over 1, just to make sure that I'm getting all of my numerators lined up and denominators lined up. But now I can see that I've got cosine squared x over cosine squared x times sine of x. And now those cosine squared x's cancel. Those just give us a 1. No need to write that. So what we get here is 1 over the sine of x, which is equal to the cosecant of x. So there we go. We have rewritten this expression into a single trig function with no fractions. All right, looking at this next one here, a little more tricky looking, so maybe we get some different strategies, but let's find out. We'll switch colors. It says cosine of theta over 1 plus sine theta is equal to the tangent of theta. So I think a good first strategy here is just to rewrite things. We're going to rewrite tangent theta. So let's keep cosine theta over 1 plus sine theta. And then we'll rewrite tangent theta with its quotient identity as sine of theta over cosine theta. So now I think to add these together, we need to get a single fraction. So we're going to have to get a common denominator here. So my common denominator, I'm going to need a cosine theta over cosine theta on the left-hand side. And on the right-hand side, I'm going to need a 1 plus sine theta over 1 plus sine theta in order to get that into the denominator. So just a couple of forms of 1 here. Maybe I'll put some parentheses on here to help me remember to distribute once I multiply things out here. But in my next step, I think that I'm getting cosine squared theta over cosine theta times 1 plus sine theta. I'm not going to multiply that out quite yet, just because we might see something that cancels with the numerator and the denominator, so keeping things factored in the denominator might be an advantage here. And then we'll have plus, I will distribute this as I write it. We're going to get sine theta plus sine squared theta all over our common denominator now, and I could have maybe just written this over the common denominator to start with, but I didn't want to skip too many steps here. So now that we have our common denominator, we could rewrite this, and I'm going to maybe change the order as I'm writing things here. I could write this as sine theta starting over here plus sine squared theta plus cosine theta. So cosine squared theta, rather, all over our common denominator of cosine theta times 1 plus sine theta. And now I see that there is a Pythagorean identity in here. Sine squared theta plus cosine squared theta, this is just equal to 1. So what we have now is sine theta plus 1 over cosine theta times 1 plus sine theta. Well, how about that? 1 plus sine theta on the bottom and 1 plus sine theta on the top. It's just written in a different order, but commutative property of addition there says that those are the same thing. So what we get here is 1 over the cosine of theta, which happens to be the secant of theta. So there we go. A lot of work there to all get down to the secant of theta, but that's what we get. So we have simplified this trigonometric expression over here, and we've just gotten it down to the secant of theta. So next we are going to simplify this with no fractions, but now it says the answer doesn't need to be in a single trigonometric function. So maybe we have a couple trig functions being multiplied or maybe added or subtracted, but we need to make sure that there's no fractions. So we'll get all the division out of here. What I see here is we have a bunch of tangents and we've got some sines. But if you look carefully, if we think about maybe the tangent of t being equal to x, I'm just making this definition here so that I can rewrite tangent squared of t minus 1 as just x squared minus 1, and this makes it maybe clearer that what we're dealing with here in the numerator is a difference of squares. I could rewrite that numerator there as, well, how I've rewritten it in terms of x as x plus 1, x minus 1. But since I've defined x to be the tangent of t, how I can write this now is the tangent of t plus 1 times the tangent of t minus 1. And that is how we can rewrite the numerator here. So now I'm thinking about factoring. Is there some factoring that I could do with this here? So that's what I'm seeing, and I can see that I can factor a sign out of the denominator. So that is where my head is at right now with these ones. Okay, just clearing off the screen now to start fresh, we can see that we can rewrite our numerator as the tangent of t plus 1 times the tangent of t minus 1 all over, and we notice that we can factor a sine of t out of both terms in the denominator here. So we're going to factor out the sine of t, and what we're left with is the tangent of t plus 1. And here we notice that we can cancel out this tangent of t plus 1 and this tangent of t plus 1. And what we're left with is going to be just the tangent of t minus 1 over the sine of t. So we are asked to write this with no fractions, so right now we still have this denominator. So I think my strategy here is going to be to see if I can't split this apart into the difference of two fractions using this common denominator here. So this is a strategy that is very helpful, and I think it makes sense going from what we'll see right to left instead of left to right, but there is no direction to equality. If things are equal, they are equal either way you look at it. So what I'm going to do here is write this as the tangent of t over sine of t, since that is going to be our common denominator, minus 1 over the sine of t. So if you think about going from right to left and think about how fractions subtract, well, we've got a common denominator of the sine of t, so we would just subtract the numerators. We would just get the tangent of t minus 1, which is what we have here. So if you think about going right to left, this maybe makes a little bit more sense, but we can use the same strategy to break apart a fraction over the numerator with just that common denominator if we find it helpful, and I think that we will find it helpful here. So if I look at my next step here, I'm going to rewrite the tangent of t in terms of sines and cosines. It's going to give us a complex fraction, but then we can look at simplifying that. So rewriting this tangent of t here as sine of t over cosine of t all over the sine of t minus, now I can rewrite 1 over sine of t as just cosecant of t. And then if I think about this complex fraction over here, this gives us sine of t over cosine of t times the reciprocal of the denominator here, 1 over sine of t minus the cosecant of t. These sines of t cancel, and we get 1 over the cosine of t, which is the secant of t minus the cosecant of t. So there we go. We have simplified it with no more fractions. We don't have a single trig function, but that's okay. We've got secant of t minus cosecant of t here. All right, so moving forward, what we were doing in those previous examples was just simplifying expressions based on whatever the instructions were asking us to do. Here we want to start verifying each identity, and this was something that we were doing with those fundamental ones before, but now they are just weirder, and these aren't necessarily fundamental identities, they are just true identities, and there's not something that you need to memorize. If you have the fundamental ones memorized, then we can use them to do any other identity that we want to show here. So the strategy for these is to pick one side, do some work on it, and see if we can't turn it into the other side here. So we usually start with the more complicated looking side. So I'm going to start with the tangent of theta over the cosine, the tangent of theta times the cosine of theta. And I want to see if I can't do something to turn it into the sine of theta. So I'm going to keep sine of theta in my head as our end goal here. So the first thing I'm going to do is just rewrite tangent of theta in terms of sines and cosines. So tangent of theta is sine of theta over cosine theta. And we're multiplying this by cosine theta. And I can write that over 1 just to keep some fractions here. And then I can cancel out these cosine thetas. And what we get is sine of theta. There we go. That one doesn't take too long, but sometimes I'll just put a little check mark or something there just to say, okay, I verified this identity. I got what I was trying to get back here. Taking a look at this next one, we see that there's some products here. 1 plus the sine of x, 1 plus the sine of negative x, and we're going to, where we claim that this is equal to the cosine squared of x. So let's see what we can do here. The first thing I notice is this negative x in the argument, so I'm going to deal with that first. We've got 1 plus the sine of x times 1 plus, actually 1 minus, because we're doing the using the odd property of sine to write this as 1 minus sine of x. So taking this negative and plopping it in front of this sine function, we've got plus negative sine, so that gives us minus sine of x here. And we don't want to say equal. We're not saying is equal to cosine of x, cosine squared of x. We are showing that this is equal to cosine squared of x. So no equal sign quite yet. We'll do equals as we simplify the left-hand side here. So now we'll think about distributing. We're going to have 1 times 1, which is 1. I'm noticing we have a difference of squares here, so this is going to give me negative sine of x positive sine of x, those are going to cancel out, and then we're going to have minus sine squared of x. And this is a rearrangement of one of our fundamental Pythagorean identities. Remember that the cosine squared of theta, or of x, since we're dealing with x's here, plus the sine squared of x is equal to 1. And if I subtract, what do I want to do here? Sine squared from both sides, we would get that, I'm sorry, cosine squared from both sides. We would get, no, sine's what I wanted. We'll get that cosine squared of x is equal to 1 minus the sine squared of x. So here is just a rearrangement of the fundamental, or of the Pythagorean identity here. So now we can see that this is equal to the cosine squared of x. So there we go. This is what we were trying to show the whole time, and we have verified this identity. All right, for this next one, we want to show that this quotient on the left, secant squared theta minus 1 over secant squared theta is equal to sine squared theta. So we're going to start with the more complicated looking side here, which is the secant squared theta minus 1 over secant squared theta side, and just use some of these identities to see if we can't turn this into sine squared theta at the end. The first thing I actually notice here is that the numerator is a rearrangement of one of our fundamental trig identities. So remember that 1 plus the tangent squared theta is equal to the secant squared theta. And if I subtract 1 from both sides here, we would get that tangent squared theta is equal to secant squared theta minus 1, which is what we have in the numerator over here. So I'm going to start by rewriting our numerator as secant squared theta. I'm sorry, tangent squared theta. We have secant squared theta minus 1, so I can rewrite that as tangent squared theta over secant squared theta. So that's my first step here. Now I'm going to write things in terms of either sines and cosines, using either the quotient or the reciprocal identities here. So tangent squared theta I can rewrite as sine squared theta over cosine squared theta. And then I can rewrite secant squared theta as 1 over cosine squared theta. Now I've got this complex fraction here. So I can rewrite this in terms of multiplication with sine squared theta over cosine squared theta times the reciprocal of our denominator, which is cosine squared theta over 1. Those cosine squared thetas cancel out, and we get sine squared theta, which is what we were trying to find this whole time. So we have verified this identity now, that the expression on the left is exactly the same as the expression on the right there. All right, here we will verify this identity here. I see, again, that there's some negative arguments here, but we need to be careful because there's also some squaring that's going on in terms of these sines and cosines. So we do need to be a little bit careful here. So let me maybe just first remind you, and we saw this earlier, that sine squared of negative theta can be rewritten as sine of negative theta, all being squared. And from that, we want to subtract the cosine of negative theta, all being squared. So putting the square next to the cosine or sine visually can kind of lead us maybe down the wrong path if we don't think about what's going on in terms of the even and oddness here, and then squaring things after dealing with the even and odd properties here. And then I can rewrite this all over, and I can maybe think about, well, let's just for now keep things how they're written, and then I'll talk about dealing with these negative arguments in the next step. So this is what we have currently. Now, we can use the even and odd properties of sine and cosine to rewrite this as the negative sine of theta, all being squared, minus the cosine of theta, all being squared. So for sine, you can think about moving the negative to the front. For cosine, you can think about ignoring the negative. Just, I mean, that's a loose way to think about it, but this is essentially the result from what we saw before. And then I can also think about rewriting sine of negative theta in the denominator as the negative sine of theta, and then minus just cosine of theta. in the denominator there, so just using the even and odd properties there. Now, if I square the negative sine of theta, that is the same as the sine of theta squared. Either way, we're going to get a positive result. So I can rewrite that way, and then this is still minus the cosine of theta being squared. And in the denominator, I can factor out a negative. I can write -1 times sine of theta plus cosine of theta now. So just moving this to the top, I can rewrite our numerator now as the sine squared of theta minus the cosine squared of theta all over negative sine theta plus cosine theta. So the numerator now is looking like possibly it's a rearrangement of one of our identities, but we can see that it actually isn't. What we know is that the sine squared theta plus the cosine squared theta is equal to 1. The fact that there's a subtraction there means that we can't use this identity. It's not the same. Here we have a plus, here we have a minus. Those are different things. But what we do have is a difference of squares in the numerator here. So we can't use that, so we'll get rid of it. But I just wanted to show you that it was different than what we want. But I can factor the numerator using a difference of squares. Oops, let me switch back to yellow. That the numerator is just sine theta plus cosine theta times sine theta minus cosine theta. And this is all over negative sine theta plus cosine theta. Now I see that this sine theta, cosine theta, or sine theta plus cosine theta cancels with this sine theta plus cosine theta. And what we're left with is we have a -1 in the numerator, so we're getting in the denominator, and we can just put it in the numerator, negative sine of theta minus cosine of theta, which is looking pretty close to what we're trying to get here if I distribute the negative now. Thinking about maybe applying it to the negative cosine of theta first, we would get positive cosine of theta, and then multiplying it by the sine of theta will give us negative sine of theta, which is what we were looking for this whole time over there. So you don't have to draw these arrows. I'm just drawing them now to clearly show what we're trying to show. So there we go. We have verified this identity. So the point of this one was to be very careful when you're squaring negative arguments. There's a potential to do things incorrectly there just based on that notation. So. All right, let's take a look at this next identity here. 1 minus the cosine squared of x times 1 plus the cotangent squared of x we're claiming that this is equal to 1. So let's take a look here, and there's different ways that we can approach this one. I did it one way, and then I took a look at the way the book was doing it, and they were doing it a different way. So I think it's valid to look at both ways here. But I'm starting with the more complicated side, and I'm going to see if I can't turn it into 1 using some of these fundamental identities. So what I'm noticing here is that 1 minus the cosine squared of x is the same as the sine squared of x, and that 1 plus the cotangent squared of x is the same as the cosecant squared of x. So those are just using the Pythagorean identities. And then I can rewrite this as sine squared x times 1 over the sine squared x using the reciprocal identity. Those cancel, and we're left with just 1. So there we go. If I notice these Pythagorean identities straight ahead, then we can get this to fall into our laps pretty quickly. But let's say we didn't notice both of those Pythagorean identities. We would still have to notice that the first half here is sine squared x. So just trying this one more time, we would still have to notice, hopefully, that this is sine squared x. But let's say that we didn't notice that 1 plus the cotangent squared of x was the cosecant squared of x. Well, okay, we'll just approach it some different way here. What we're going to do is multiply this by 1 plus, and I could rewrite cotangent squared x as cosine squared x over sine squared x. And now we can maybe think about let's think about distributing the sine squared x inside here. This is even a different way than the way I have it in front of me. So now that we have 3 different ways, but I think that this is a little bit more intuitive here. We're going to end up with sine squared x plus sine squared x cosine squared x all over sine squared x. And now these sine squared x's will cancel. And we've got sine squared x plus cosine squared x, and that is equal to 1 using the trig identity there. So a couple different ways that we could verify this identity. It's not that every way has to go exactly the same. People could do them different ways, but we should be able to get to the end result no matter what. So just a summary here, some guidelines for verifying a trigonometric identity. And I tried to kind of say this out loud as I was going through examples. Work with one side of the equation, usually the more complicated side, and keep the other side in mind as the final goal. As you're making decisions on what you should do, you should be working towards your final goal. Look for opportunities to apply the fundamental identities. If the expression is a product or a quotient of factors, consider the reciprocal or the quotient identities. If there's a squared term in there somewhere, see if you can't use one of the Pythagorean identities, and you might need to rearrange things a little bit. If the expression involves a negative argument, consider using the odd and even identities. Be careful if there's some squaring going on in there. And then you just want to apply basic algebraic techniques. You want to think about factoring, multiplying, combining like terms, getting a common denominator, and then simplifying complex fractions. I notice that there's a lot of complex fractions that happen when you're going through these. And then consider writing expressions explicitly in terms of sine and cosine. So if you get something like a cotangent or even like a reciprocal 1 over cosecant or something, you can try and write things in terms of sine and cosine. And if you get stuck on one side of the equation, consider going to the other side, the easier side, and seeing if you can't change that in some way to turn it in and meet in the middle somewhere. So sometimes you just start working down the easier side and you get stuck. So you start with maybe the easier, I don't know if I said that right, start with the harder side until you get stuck, and then maybe look at the easy side and see if you can't manipulate that so that they meet in the middle somewhere. And that is a valid way to kind of come back around and find your final argument here. So that is just a summary of guidelines here to help you work through these problems. So with that, it is time to practice. So good luck with the homework. If you need any help, please let me know. I'm always here to help you, and I'll see you in our next video.